Determining of instantaneous center of velocities. Article 8.5 of the book Mechanical Systems Calculations of the Marine Facilities. We will keep studying the use of the concepts of the flat motion, of kinematics of the flat motion, of the velocities in the flat motion, and how to use this in the calculations, in the determinations of the characteristics of the mechanical systems, of the elemental mechanical systems. So there's example of the flat motion of the mechanical systems, for which is very relevant to use the concepts of the instantaneous center of the velocities. On the figure 8.5.1 is shown the connecting rod and the crank mechanism. So we have slider here and the connecting rod and the crank to find the dependence of the elements of the motion of this mechanism. The concept of the instantaneous center of velocities can be used for this one segment or 008, yeah, the crank or the connecting rod AB and the slider, or two sliders with the connecting rod. We have the find here the center of the velocities instantaneous. For example, for here, the center of velocities for the crank is 0, the hinge, yes. For the this is for the crank, and for the connecting rod, if we have the direction by the tangent of the point A around the point 0, we can find that inclined tangent, and by the perpendicular, keeping the straight line 0, A, etc., we will have the perpendicular to the direction of the hinge A with the crank, and in the intersection of the perpendicular to the line of the motion of the slider B here, anyway up here, we can find in the intersection the instantaneous center of the velocities for the connecting rod, and to find the velocity of the point B, for example, if we have the velocity of the point A. Epsograph rule, another one example, the instantaneous center of the velocities for the connecting rod A and B is in the intersection of the perpendiculars. Here we can have the perpendicular to the direction of the velocity of the slider A, and here we have the vertical perpendicular to the direction of the velocity of the point B, and the intersection we have the instantaneous center of the velocities of the connecting rod AB. So we can have in these two velocities to find all other elements having the with the velocity assigned, for example VA. We can find the angular velocity of this connecting rod. We can find the velocity B having the point of the intersection of two perpendiculars here, which is the instantaneous center of the velocities. The wheel, the rolling wheel, here we have the instantaneous center of the velocity is the point of the support at A, here we have 8.5 to A. This is P. P is the instantaneous center of the velocities of a rolling wheel, and this is distribution of the velocities. The velocity of the point A, VA, we have velocity point C. The velocity is VC, and VA is twice bigger, just because from the instantaneous center of the velocities, it is like the diagram, the velocity distributes linearly independence of the distance from the instantaneous center of velocity. In definite cases, P. We can find as well the direction of the velocity of the point B, and the magnitude of the point B, just vector VB, we can find as well. This is another one example in which we can use the concept of the instantaneous center of the velocity. So about the definition of the motion of the physical body of flat motion, the physical body of flat motion is that all points of the physical body moved in the parallel with definite fixed plane, unit one with definite one fixed plane. This is a flat motion of the body. So the elements of the wheel motion. Yeah, this is about the wheel we had here, the wheel figure H.5.2b. Elements of the wheel motion, the angular velocity assigned omega, and translational velocities we can find of the points A and the B. They are, as we have the, we can find the omega even if we have the translational velocity of the center, the point C, and the radius, the distance between the point C and the point P. And the P, that's the point of the support of the wheel. The angular velocity is the ratio of VC to the arm CP, VA. The velocity is the angular translational velocity of the point A. Or the point A is product of the angular velocity got as VC divided by CP, the arm. The velocity of the point A equal to the angular velocity multiplied by the AP. AP is twice bigger than the CP as a diameter. And the direction of VA and vector is perpendicular to the arm AP, and the VB is a point on the left here on the indicated drawing of point B. The velocity here we have in the direction of the velocity is perpendicular to the radius BP based on the instantaneous center of the velocities. And to assign the flat motion of the body, we have to specify usually we can use a parametric equation or just a vector form. Vector form about the same as a parametric equation of assigning of the plane motion, or by the other ways. But actually, the most relevant is the assigning of the parametric dependencies. For the plane motion of the body, we have to define not only the motion of definite one point, but as well the rotation. There's one point, maybe another one point, perhaps the point A. And we have the parametric equations. We have to have the parametric equations xa dependent on time and ya dependent on time. And besides, we have to have the dependence of the angle of the location of any segment within the body dependent on time as the angle, because we will confine the derivatives. Derivative will be with velocities. It's a derivative by time of the phi angle is angular velocity of rotation of the in the flat motion of the body, and the derivatives of the coordinates xa and ya are the components of the velocity on the axis x and y. The velocity of some other point of the body in the plane motion of the body one can find as any other point can we define the motion, probably the point B as the velocity of the point A plus velocity of point B relative to the point A. And the velocity of the point B we can find as the product of the angular velocity by the radius AB, and the relative velocity of the point B relative to the point A is perpendicular to the radius AB. And the projections of the velocity of the point A, the first derivative of on the axis abscissa and on the ordinate axis y is the first derivative of ya, and the total magnitude of the velocity we can find by the Pythagorean theorem as the square root of the two squared components of the velocity of the point A. The instantaneous center of the velocities, the point P. Here we have the point P. Here could be outside the body, but it's not so much important. But we can find as just the intersection of the perpendiculars to the points, perpendicular to the directions of the point of the velocities, of translational velocities, and these 2 points we can find the instantaneous center of the velocities. It's located in the intersection of perpendiculars to the velocity vectors, these points A and B. So we have 2 perpendiculars here on the sample C, for example, here. Angular velocity equals to as a just a ratio of the translational velocity of any point to the appropriate radius, maybe BP or maybe AP. Radius as well as we can here. The properties. The first is both of the points of the rotating body A and B lie on the common perpendicular to the velocity VA and VB. This is shown on the figure 8.5.4a. Then the A and B. Then the position of the instantaneous velocity center with respect to these points corresponds to the proportion. So the velocities, we have the same perpendicular. The points are on the same perpendicular, and the velocities perpendicular to the definite line ABP. And the distances AP and the BP are in the proportion of the velocities VA and VB. The same we have here, but point P, the instantaneous center of the velocities for this different one case, located outside the segment AB. Here, the P is in between AB and within the segment AB inside. And perhaps we even don't know the, we have not the second point, but we have the angular velocity too. So we can find by on the perpendicular the instantaneous center of the velocity, because we can find on the other hand the length of the segment AP, like a radius or the rotation of the instantaneous radius of the rotation of this body in the flat motion. The radius AP is equal velocity of translational divided by the angular velocity VA divided by omega. Besides more properties, we have the circumstances of location on the at infinity of instantaneous center of the velocity. So if we have two points with the constant velocities on the same perpendicular, so the velocities are the same of the VA and VB, then the point of the intersection of the line connecting these 2 points and line connecting the ends of vectors of the translational velocities of these 2 points in the mechanical body, the point of the intersection is in infinity. So this mechanical body moves with not a rotational velocity. The same here. If we have 2 parallel forces and 2 perpendiculars to the parallel forces, these perpendiculars do not intersect. Exactly these forces, these velocities, not forces, velocities are of the same magnitude, yes, because are they not possible for the rigid body. But anyway, we have 2 parallel perpendiculars in between. They are parallel. They intersect in the infinity. So the motion of this body on the example H55B is that the body moves with not the rotation. The distance is we divide the velocity to the we have zero angular velocity. The distance from the point to the instantaneous center of velocity will be infinity. If you divide to 0, it could be the infinity distance to the instantaneous center of the velocity. Let's consider exercise. The epicyclic mechanism is shown on the figure, the flat mechanism, figure 856. Consists of 2 wheels of the same radius. We have 2 wheels, one fixed wheel, one, and the second is moving wheel around the first one fixed wheel, moving by the crank. And we have the crank, we have a hinge, the hinge connected by the connecting rod with the slider 5. Now, this crank 0A rotates with around the point 0 with assigned velocity omega. It is issued to find the velocity of the slider 5. So let's consider the epicyclic mechanism consequently. So first, the velocity of the point A, the velocity of this one point A, this point A, we can find as we consider this crank. The crank is number 3. So from the point 0 to point A, the length of the crank is 2 radiuses, because we have the same wheels. This one radius, the second one radius. So this velocity of the point A equal to the product of 2 omega angular velocity of the rotation of the crank around the point 0 multiplied by radius. 2 radius is distance 0A. The instantaneous velocity of center of moving wheel is located in the point P. Point P because this one fixed wheel, and this wheel goes around the fixed one. That's why the angular velocity of the wheel 2 is equal to V of the translational velocity of the point A divided by AP. AP is R, so we can, from this one, we can divide by 2 omega R, this velocity of the point A divided by radius AP. So AP equal to R. So we have 2 omegas, angular velocity of the second wheel, the velocity of the point B moving wheel, this 1 second wheel, equals the omega 2, there's 2 omegas, the angular velocity of rotating of the second wheel, multiplied by the BP. BP is the radius from the instantaneous center of the velocity of the second wheel. And the distance to the point B, the radius is 2r. So we have 2 omegas is the angular velocity of the second wheel multiplied by 2r. 2r is a distance, a diameter, twice bigger than the radius of this definite one wheel. So we have 4 omegas by r. The velocity of the point. Same mechanism position indicated on the diagram. We have 2 points here. This one goes parallel to the horizontal axis, and we have the perpendicular vertical. This velocity as well as parallel. So this whole connecting rod moves just translationally, moves to the right in this definite one scheme of the mechanism. So the velocity of the point C equal to the velocity of the point B and equal to 4 by multiplied by omega by r. This is the result of the finding of the velocity of the point C. Sorry. Next exercise. Exercise 2. A square body with this idea undergoes a plane motion. So we have the definite square body shown on the figure 857 A and B. So it is required to find the velocity of the point B, assigned the velocity of the point A, which is VA, and the angular velocity of the rotation of this square in the flat motion. The velocity VB of the point B equals to this velocity equals to the product omega angular velocity assigned on the size BP, and instantaneous radius BP is of the curvilinear motion of the point B is BP equal to square this with right angle triangle square root of the diagonal of the this one square, and diagonal and square is 1 leg of 2 right angle triangle, and plus the squared second leg. Second leg is the radius PA from the instantaneous center of the velocity P to the point A, and the size of the radius AP we can find considering the rotation. So this point moves with the velocity A, and we have angular velocity, and we can find the radius as we divide the translational velocity by the angular velocity. We can find AP. So here under the square root of the second summit, we have the ratio of the translational velocity of the point A by the angular velocity of this square body. But this second summit is 2 square power. This is exactly because this is a Pythagorean theorem, as we consider the total of the 2 squares of the legs. This is 2 by d squared. The 2 is because the AB diagonal of the square is d, the size of the square, multiplied by square root of 2. This is very understandable, so let's keep going. Exercise 3. The square body, the same square body with shown on the previous one. Figure with side 4 meter makes a plane motion. The sine moment of the angular velocity is equal 1 second minus 1 degree, 1 radian per second. And the velocity vector VA of the vertex A is directed along the body diagonal equal to 3 meters per second. We have to find the velocity of the point B. This is about the same. The first solution, the use of the velocities addition theorem. So if we consider 2 components, velocities VA and velocity of the point B by the rotational motion around the point A. So the VA we have 3 meters assigned, and the velocity of the point B is around the point A is the diagonal AB multiplied by omega. This is 5.66 multiplied by 1. Excuse me, omega assigned 1, and AB is 566 meters because the diagonal of the square AB is d d is assigned 4 meter, so d is 4 meter, yeah, 4 meter assigned, yeah. Okay, second solution. The first decision is 6.5. Second solution, the use of the found distance Vp to the instantaneous velocity center. So first we can find the radius between the point A and the point P, this distance AP. AP is equal to the translational velocity. We did that previously. VA 3 divided by 1 equal 3 meter. BP equal to the 566, the velocity of the point. The 566 is the geometric characteristic of the. Oh, no. Yeah, 566 meter is AB size, 566 squared plus AP plus 3 meter squared. 3 meter we got here by considering the translational velocity of the point A and the angular velocity of the mechanical body. So we have 6.4 meter BP size, and the VB equal in the rotation of the point B relative not the point A but relative to the point P, with not the relation of B to A. So just immediately B motion to the instantaneous center velocity is point P. So we have 2/6 by the angular velocity of the radius BP. So we have 6.4 meters. So solution, the theorem use of the projection velocities of 2 points onto the segment connecting these points. Yes, so we have velocity VA and we have the velocity of the point B, and the projection of the point B, this is the projection VA. So this horizontal is VA. So the projections of all points of this mechanical body along this line of the velocity VA have to be the same. So we have to find the magnitude of the velocity VB. Just have to consider the projection on the abscissa axis and the angle. This is the same angle, or this one angle we can find here, having this right angle triangle. So we can find that this VB equal to VA divided by cosine of the adjacent angle. This is diagonal of the right angle triangle. This we equal to not the leg and divided by the cosine of the adjacent angle between the leg and between this diagonal. So we can find the cosine as AP divided by BP. This is 3 divided by 6.4. So this is from this angle. This is 3 meter divided by this distance is 6.4. So we can divide 3 divided to 6.4. We'll find this cosine of this angle. The angle is the same as this one angle. So we can find the VB as VA the same as the VA of this one, because of this, the projection of the same line of these points. And we can find that having the cosine as 0.469, we can find that VA equal to VB by cosine alpha, and we divided, we can find that VB equal to 6.4 meter, as VA is 3 meter per second. So questions and comments. Plane motion of the rigid body in which all points of the body move parallel to a certain fixed plane. Yeah, this is the definition. What is the plane motion when the all points on the body move parallel to a certain fixed plane? Second definition, 8.5.2, the instantaneous center of velocities in the plane motion of rigid body is a point whose velocity is 0 in the plane of the, yeah, it is. This point can be within the space of the body or can be outside the body. H53 elements of the wheel roll in the flat motion. The angular velocity of the wheel rotation, translational velocity of the wheel axis, and other points. Yeah, if a wheel moves over the surface, the instantaneous center velocity, the point of the support of the wheel on the surface, and the angular velocity equals to the ratio of the velocity of the axis of translational velocity of the axis of the wheel to the radius of the wheel. And other points, velocities, translational depend on the distances, on the radiuses from the instantaneous center velocities to this point. So the upper one point of the wheel velocity is twice bigger than the velocity of the axis, I mean translational velocities, because the distance from the instantaneous center of the velocities to the upper point of the wheel is equal to diameter, that is 2 radiuses, and the distance between the supporting point, that is the instantaneous center of the velocities of the rolling wheel, to the axis of the wheel is equal to just only 1 radius, so the velocity of the upper point is twice bigger. 854. The coordinate assignment of plane motion of body by specification the motion velocity of any point of the body and the velocity of the body rotation. Yeah, we to define the motion of the body. If we compare with the definition of the motion of the material point, we have to specify two parametric dependencies of each of the coordinates change by on time. And if we are talking about the body, besides of the change of definite one point coordinates, parametric dependencies, we have to have another more parametric equation of the change of the angle of the inclination of the any segment within the rigid body to the axis of coordinate. So we have three parametric equations of dependencies on time of the projections of the location of any point of the mechanical body, and the third equation of dependence of the inclining of any segment within the body to the coordinate axis. H5 for the coordinate assigned the plane motion, the body specification of the motion velocity to any point of body, the velocity of body rotation. Yeah, that is the same. Oh, H55. In the general case, finding the instantaneous center of velocities for plane motion of the body at the intersection of lines drawn the points of the body perpendicular to velocities of these points. Yes, if for the body moving, flat moving of the body with the rotation, the center of velocities is, if we have the velocities translation of two points of the mechanical body, the instantaneous center of the velocities will be in the intersection of two perpendiculars from both of the points perpendiculars to the vectors of the velocities of these points. If the body moves with the rotation, these perpendiculars intersect in the point of the instantaneous center of the velocity. 856, if the points of the body move in parallel at different velocities, then the instantaneous center of the velocity is located on the line passing through these points, and when they are perpendicular to the velocity vectors of these points, when they intersects with the line passing by the ends of the velocity vectors. Yes, if the points are on the same line, and so that is the motion of they move in the one direction or in other directions with other velocities, so we can consider not only the line of the location of the points of the considered point, but as well the line connecting the ends, the straight line connecting the ends of the velocities to these points. The intersection of two lines of the connection these points and the line connection the ends of the vectors of the velocities translation of these points, intersection of two lines gives us the instantaneous center of the velocity. The 857, the instantaneous center of velocities is located on a line perpendicular to the velocity center of the point in a plane motion of the body at the distance equal to translational velocity of the point divided by the angular velocity of the body, if the this distance is set aside from the direction of the velocity when turning at right angle in the direction of the angular velocity. If we have only one point and we have the velocity of one point of the body, and we have the angular velocity of the all bodies, all points of the body, angular velocities, then the instantaneous center velocity we can find at the perpendicular of on the perpendicular to this point at this point perpendicular to the direction of the velocity of this point at the distance equal to this velocity divided by angular velocity of the mechanical body rotation. Then to one or to other one direction of this perpendicular, we can find the instantaneous center of the velocity. The direction of location is it to the right or to the left by the perpendicular to the velocity direction. perpendicular at the point of the considered point, which velocity we know, the direction to the right or to the left depends on the angular velocity direction. 858. In the instantaneous translational motion of the body, when the velocities of 2 points of the body line on the perpendicular to the velocity vectors of one side, or when different perpendiculars, those different points are parallel to each other, the instantaneous center of the velocities is located at infinity. Yes, it is. If the mechanical body is of zero angular velocity, then all points, perhaps the moving body with definite translational velocities of the points of the mechanical body equal for all points of the mechanical body and directed in the one direction. So we have no the instantaneous center of velocity as this all body moves progressive, move translational, so it's not rotation. This understood. Thank you.